Hello, I have been given worksheet B, so I'm going to go through the questions and how to answer them. The first question says, a helium neon laser emits red light of wavelengths 6.3 times 10 to the power minus 7 meters. Show that the energy of a single photon is about 3 times 10 to the minus 19 joules. Right, for this question, we use the Einstein equation. Energy of a photon equals the Planck's constant multiplied by the speed of light, which is what speed electromagnetic radiation travels at, divided by the wavelength. So simply, the Planck's constant is 6.63 times 10 to the minus 34 joule seconds, multiplied by 3 times 10 to the power 8 meters per second, divided by the wavelength, which is given as 6.3 times 10 to the minus 7 meters, which gives you the final answer, when rounded, of 3 times 10 to the minus 19 joules. Okay, so question 2. The power of the laser beam is 1 milliwatt. Show that about 3 times 10 to the power 15 photons are emitted by the laser each second. So 1 milliwatt is 0.001 watts, and a watt is equivalent to a joule per second. So we have 0.001 joules per second. So if there's that many joules available, how many photons can be emitted for that number of joules? We just divide that by the number of photons. The energy. Yes, we do that divided by 10 to the power 15, which gives 3.3 times 10 to the 15, which when rounded gives our answer of 3 times 10 to the 15. The next question, the photons of red light are emitted by neon atoms in the gas inside the laser. Explain what energy levels are and how they can be used to describe the emission of photons from atoms. So for this question, I explained that if we have a nucleus, we have distinct, this is the simplified drawing of the atom, we have distinct, discrete energy levels that electrons can occupy. And electrons have different energy depending on which orbital they occupy. Therefore, if energy is given to a particular atom, say in the form of a photon, then the electrons may gain energy and jump to a higher orbital, a higher energy orbital. When they return to the electron is now in a higher orbital, and when it returns back down to its original orbital, it has to emit that energy. And in this case, the energy is emitted as a photon. So that explains that question. The next question, another laser emits blue light. The power in its beam is also 1 milliwatt. Explain why the laser emitting blue light emits fewer photons per second compared with the laser of the same power emitting red light. Well, according to E equals hf, which is energy of a photon equals the Planck's constant times by the frequency, blue light has a greater wavelength than red light. So the Planck's constant remains the same. If the frequency increases, the energy must also increase. So if the photons have greater energy, then less may be produced by the blue laser for the same power. Moving on to question B. A photodiode is a circuit component which can be used to convert a light signal into an electrical one. Figure 7.1, the diagram, I'll show you the diagram. Shows an enlarged cross-section through a photodiode to illustrate how it's constructed. Light is incident on the transparent conducting surface layer of the diode, and light passes through to be absorbed in the insulating layer. The energy of each photon is sufficient to release one electron in the insulating layer. The potential difference V applied across the insulating layer causes these electrons to move to one of the conducting layers. Draw an arrow on figure 7.1 to show the direction of a motion of an electron released at a point X in the center of the insulating layer. So if an electron is released at point X, it will move round the circuit towards the positive end of the battery because obviously electrons are attracted to positive charge. The next question, the red light from the laser in A is incident on the photodiode. Experiments show that only 20% of red light photons release electrons in the insulating layer and hence in the circuit of figure 7.1. Calculate the current through the photodiode. Right, so if 20% of photons, so 20% times by the number of photons per second gives this answer, 6 times 10 to the 14 electrons. So, according to current is equal to charge over time, the charge is equivalent to that many electrons times by the elementary charge E. So 6 times 10 to the 4, which is the number of electrons, multiplied by the elementary charge, which is 1.6 times 10 to the power of minus 19, is equal to 9.6 times 10 to the minus 5 coulombs. Therefore, the current is that charge divided by time, which is 1 second. So current is also 9.6 times 10 to the minus 5 amps. And the final question suggests one reason why the efficiency of the photodiode is less than 100%. I've simply said that some incident light energy is not absorbed in the insulating layer. Thank you for my cameraman, David.